Gayatri, can you hear me?
Yes, sir.
Okay, so Gayatri, I was wondering, how are we going to live stream it on YouTube?
Meaning?
Like, for example, the video will be recorded, right? You will record the video, right? Once
Yeah.
once he joins in or something like that, right?
Yeah.
Okay, and so that will be that usually when you join over Zoom and then if the video is recorded, the speaker is usually notified. So that is going to happen also, right? So he has to say yes or something, right?
I don't understand what you're telling, sir.
So usually, let's say that if somebody is recording the video, the host usually, right?
Yeah, he will know. He'll be notified.
He will be notified, right? So and he has to actually press yes.
No, nothing. We are the host, so he doesn't have to do anything. He'll just know that we are recording. That's it.
But I think you have to agree first and then you can enter.
No. We are the host, sir. When we are
No,
the
he can
host,
record, but it is also within his discretion to join.
I don't think so, sir. Our settings are not is not like that.
I see. Okay, fine. In that case,
He'll just be notified that it is being recorded. That's it.
okay. And the YouTube will start once the talk starts, right? Or something like that. Yeah?
Yeah.
Okay, fine. Hi, good morning, madam.
Hi, how are you?
Good, how are you?
Fine, thank you. We are all set.
Yeah, we are all set, yes.
Should I share now or
Yeah,
later?
you can keep it like shared or just we can check anyway. We checked yesterday, so I think it should be all right. Yeah. So the way what I will do is I will just give a very short, brief introduction to the program itself, which will take like a minute perhaps, and then I will introduce you, and I will also give the citations that was given by the commission of the stat fees, and then of course you can go ahead. And I wanted to ask you that when would you like to take the questions? Do you want to have them intermittently? Do you want to have them at the end? Like this should...
Both. Yeah, I think intermittent is fine.
Okay, sure.
Happy to be interrupted. I'll keep an eye on somewhere to know that there are questions,
No problem.
or you can interrupt me if there are questions and I
Yeah,
don't
so
see.
I will just maybe if there are some urgent questions, we can take them in between. Otherwise, maybe we'll just wait till the end. Something like that.
Okay.
Yeah. So we'll wait like 2
Yeah,
more.
no, usually questions in between are quite illuminating. It's good to sort of answer them at the time.
Okay, so if that is so, then I will not probably add any add any comment, like, so people are welcome to ask questions.
Yeah, exactly. Thank you.
Okay, no problem. So we'll wait like maybe another 2 minutes, and then I will start the program.
Okay.
So this will be also live streamed on YouTube through our official channel. We have an official YouTube channel. It will be live streamed through there. And once the program is over, I will share the link with you at some point of time.
Okay, no problem.
Okay. So Mehran, I think I will start the program then. Okay.
Thank you.
Okay. So hello everyone. So welcome to the Boltzmann Day. So the Boltzmann Day at the Institute of Mathematical Sciences, Chennai, is to celebrate and honor the achievements of the Boltzmann medal recipients. To give you some background, so the Boltzmann Medal or Boltzmann Award is a distinguished prize awarded to physicists for outstanding achievements in statistical physics. It is named after the physicist Ludwig Boltzmann, who is known as the father of statistical physics. So the Boltzmann Medal is awarded once every 3 years by the Commission on Statistical Physics of the International Union of Pure and Applied Physics during the StatPhys conference. Notable recipients of these prizes from previous years are Wilson, Kubo, Fisher, Kadanoff, Leibovich, Parisi, Edwards, Widom, Stanley, Cardi, Derrida, Deepak Dhar, and John Hoffield from last year. So this year, the prize was awarded to Professor Yoshiki Kuramoto from Kyoto University and Professor Mehran Kardar from MIT. So it's our great pleasure on this occasion to welcome them virtually at IMSC. So let me briefly say a few words about Professor Kardar. So Professor Kardar received his BA degree from Cambridge University, UK in 1979, and his PhD in physics from MIT in 1983. Following 3 years as a junior fellow at the Harvard Society of Fellows, he joined the faculty of MIT, where he is currently the Francis Friedman Professor of Physics. Professor Kardar has contributed to statistical physics by authoring 2 seminal textbooks in the field and conducting research spanning soft matter, biophysics, and disorder systems and non-equilibrium phenomena. His awards include the AP Sloan Fellowship, Presidential Young Investigator Award, Guggenheim Fellowship, Alexander von Humboldt Foundation Research Award. Professor Kardar is an elected fellow of the American Physical Society and the American Academy of Arts and Sciences. He is also a member of the prestigious National Academy of Sciences. So let me read out the citation from the award given by the commission this year. So Professor Mehran Kardar receives the Boltzmann Medal 2025 for groundbreaking contributions to non-equilibrium statistical physics, especially for the celebrated Kardar-Parisi-Zhang equation, the successful application of stochastic field theory to surface growth, and for demonstrating the relevance of the equation to a diversity of phenomena. Professor Kardar has been tremendously influential in a revival of theoretical studies of the Casimir effect and has achieved outstanding results in the field of soft matter, active matter, and biological systems. So without further ado, let us welcome Professor Kardar once again. Today, he is going to talk about boundaries, inclusions, and disorder in active matter. With that, over to you, Mehran.
Dear Arnab, thank you very much for the kind introduction. And I'm very grateful for you and your institute for organizing this nice event for Boltzmann Day. I would like to very much apologize for not having been able to participate as in the originally planned date. Entirely my fault, and I'm sorry for that. I'm glad that you provided me with the opportunity to do so at this later time. So I'm happy to take questions as I give my talk, so please feel free to interrupt me. I have been told that as a statistical physicist, I have to start every talk with the ideal gas. So this is supposed to be a view of the ideal gas, particles such as the particles of the gas in this room, impinging on the walls of the container. And these collisions we usually think as the origin of the pressure on the walls. But of course, the pressure really is to be taught in equilibrium as the change in the entropy as the volume of the container is changed. And even for something like salt molecules and ions in water, there is a corresponding pressure, which is really related to the entropy gained by the change of volume. As a result, the pressure that we have in equilibrium is completely independent of the shape of the container, potential at the wall, and the properties of the particle. And you have even this in the dilute limit, the ideal gas law that is completely independent of the entities and the places in which they are moving. So the question arises that nowadays that there is a lot of work on active systems, and they come in different varieties. For example, these are colloidal particles that are asymmetrically coated. So when light is shined on them, because of the asymmetry, they start to move, and you can stop and start their movements by turning on and off the light. And they also, if I put a wall, will impinge and put a pressure on the wall. There's another example, which is you can imagine that you have essentially grains on top of a surface that you're shaking, and there's experiments on this as well as simulations. And these randomly moving grains also can exert pressure on the walls of the container. And of course, the impetus for thinking about active systems usually comes from biology, where the entities in this case are living cells that also move around, and they can exert pressure on walls of a container. So the question that we asked maybe a decade or so ago is, to the extent to which this force that they exert on the walls of the container has similarities or difference from that of the pressure of the ideal gas. For this, we need a simple model, and the simple model of active particles that people have used in simulations is just a simple modification of the Langevin equation used for colloidal particles. As a reminder, the Langevin equation imagines that you have a colloidal particle that is very much damped, so its velocity is simply proportional to the force that is exerted by the potential. But there is also randomness, and this randomness is what causes the diffusion of the colloidal particle, even in the absence of the potential. And the simple modification that one does to that is to assume that these particles are active in the sense that they have an engine that tries to move them with a particular velocity in a direction indicated by theta, but this direction itself changes in some random fashion as a function of time. Either every now and then a run is followed by a tumble, which is what E. coli do, or maybe the orientation is randomly changing in angular space by diffusion. And in either case, you generate particles that are moving around. They kind of look like an ideal gas, but what kind of force do they exert on the container? To answer the latter, imagine that the potential due to the wall is something that is very steep, starts at the position of the wall and quickly goes to infinity, so that when the particles approach to the wall, because of this corresponding force, they're pushed back. Now, if this new term that we added was absent, we can solve the Langevin equation, and we know that the resulting density satisfies the usual Boltzmann weight associated with that wall. And we can calculate the force, for example, from the corresponding density by multiplying the density on approaching with the wall, the force that is the derivative of the potential exerted on the wall, integrated over all particles from interior to the edge of the wall. Now, this integral is easily doable because the potential and its derivative appear here. And the result of the integral is usually the simple ideal gas law, independent of the properties of the container. So we can ask, if we now add this additional term, what happens? And we also added one more twist, because essentially we can see that the particles on approaching the wall, they can also change their orientation. And so we model the system, rather than having circular particles, something like an elliptical particle, and the front and the back will experience different potentials on approaching the wall, and there is a corresponding torque. So the angular equation also is augmented by having a torque due to the different forces from the wall. Now, with this modification, we can solve the corresponding Fokker-Planck equation for what the density of the particles is. And the density is different from what we have in equilibrium. And typically there is an accumulation close to the wall. And we can use that calculated density to calculate what the potential is. And we find that surprisingly, well, maybe not so surprisingly, the pressure that we calculate as the force per unit area has a part that is kind of independent of the properties of the container, can be expressed in terms of an active temperature, which is related to average motions of the particles, but a part that really does depend on the forces and torques that are exerted from the wall on the particle that is approaching it. Now, the consequence of this is something like what is indicated in this movie. Imagine that you have a homogeneous density of these active particles at time zero, and then you insert at time zero a piston in the middle of this homogeneous gas, except that the piston has different properties on the two sides. One wall is maybe soft, one and the other side may be hard. And because of that, there are different pressures that are exerted on this from the active particle, and the homogeneous system spontaneously will move in one direction or the other, eventually coming to some new equilibrium where the two densities are different. Now, this is something that would clearly not happen in equilibrium for the simple reason that equilibrium system is invariant under showing the movie forward or backward in time. And if I have the wall, because of the asymmetry of the two sides in equilibrium, move to the right in the forward movie, it should move to the left in the backward movie, and the two would be inconsistent. But this is a system of active particles in which there is constant input of energy, and so the time reversal symmetry is broken at the microscopic level, and this is the macroscopic consequence of that. There are other manifestations of this. Certainly, if we put a box on a two-dimensional system where you have moving bacteria and the two sides of the box are different from each other, there is going to be a net force on the box, and the box can move in some direction. We found that this is only the case if the particles have this external, non-spherical shape, so there is a torque in addition to the force from the wall. So we were asking ourselves whether there are some circumstances where even for particles that don't experience a torque, there is something interesting that is going on. And clearly, one example that we expect to happen is when the potential at the wall is not uniform under, let's say, up-down symmetry. It has an asymmetry, and this asymmetry can generate some kind of a net force on the wall. And this is manifested very nicely in this experiment by Leonardo's group, in which a ratchet in a solution of bacteria gets to move in one direction, something that will never happen in equilibrium, because again, for time reversal symmetry, we could not distinguish going clockwise or counterclockwise if the system is time reversal symmetry. So that's another manifestation of this microscopic time reversal symmetry. Even if the wall is completely symmetric in the sense that it doesn't have ratchet effect, but it is curved. For example, the wall has a hill and a valley. What we find is that there is distinct accumulation of the particles on top of the hill and the bottom of the valley. Essentially, the particles try to penetrate more into the valley and kind of cloud outside the top of the hill. As a result of that, there is more force that is exerted here compared to there. And effectively, what we find is that the force that is locally exerted on a boundary that is curved is related to the only geometric quantity that is available, which is the curvature. And we can indeed fit that really there is a variation of the pressure with the radius of curvature. It's inverse, in fact. And this is very reminiscent of Laplace's law, in which the pressure differences across, let's say, soap membrane are related to the curvature. So effectively, it looks like the presence of activity embeds some kind of an effective surface tension, which is the coefficient that one sees in Laplace's law. And we can sort of, from our simulations, compute what that contribution is for the kind of systems that we have been simulating. Interestingly, we find that this contribution to the surface tension effectively has the negative sign, and this negative sign indicates that there is a tendency to destabilize a line from being completely stretched to something that is more curved. And this indeed has been seen in some experiments in which a chain was placed in a solution of these granular particles that were shaken, and the chain preferred to be as stretched as it could be rather than taking a straight line type of configuration. Okay. Now, an interesting consequence of this observation that the pressure depends on curvature is the movie that I will show you over here, in which we have these red particles that are active particles, and you have a solution of these active particles, in the middle of which you put a flexible filament, if you like, a worm, where the filament itself is not active, but it is pushed around through collisions with the particles. Let's see what happens. Essentially, these random collisions cause it to sort of fluctuate one way or the other, but at some point, it spontaneously happens to have curved in one direction. Once it does so, the pressures that are exerted on the two sides are different because of the curvature being positive or negative on the two sides. And effectively, this becomes itself a particle that moves, an entity that moves in a particular direction. So I kind of give this as an example of being on a sailboat in the middle of the lake, and there is no wind. But if the particles of the air are active particles, you can just curve your sail and you will create the wind that will move you in whatever direction you want. Now, of course, this is very much dependent on the flexibility and length of the chain, and the much longer chain, because of its lack of rigidity and persistence, will perform a much more complicated dance. So this was a case of a flexible chain, but clearly one can embed into the system a rigid object that has a shape of a C or a U, and this object, because of the collisions of the particles that are different on the two sides, this is another perspective of this, we will experience a net force. But what happens if we, corresponding to this net force that it experiences, if we kind of fix it to some point, there is going to be counter forces that are exerted on the fluid of these active particles around, and these counter forces will generate currents of particles. And essentially, it is easy to show that the net effect is as if one has placed at the location of this asymmetric object a kind of pump that sucks in the fluid from one direction and pushes it out from the other direction. So just placing a U-shaped or C-shaped rigid object in this fluid acts an active pump that moves the particles at the large scale through it in this fashion. And in the continuum language, since the number of these active particles is fixed, their density must satisfy some kind of a continuity equation, and the corresponding current one can show is caused by having a pump that effectively is like a dipole at the origin of this curved object. So this causes currents and density variations throughout the fluid that have characteristics of a dipole in terms of their fall off. Now, one can imagine that indeed, if one has two of these asymmetric objects, the current of one will influence the forces that are exerted on the other. And so there should be kind of long range forces between these, because all of the consequences of this conservation law of density is that the density variations, etc., are falling as a power law. Okay. Now the next, I'm happy to take questions, by the way. I don't know if I missed any question.
There was none in the chat box so far, but I think people will ask questions at the end.
Okay. So now let's keep that in mind. And what I want you to keep in mind is this U-shaped particle exerting a kind of pump-like effect on the density and currents of the active particles. And rather than having a single defect, let's imagine that we have these bacteria or active particles that we have moving on a rough surface. And because of the roughness of the surface, maybe at some locations they would like to move faster, and some locations they want to move slower, etc. Now, if I were to coarse grain from the microscopic picture, I would imagine that if I kind of look at some locality that is coarse grained, there will be on average some asymmetry that will tend to push the particles in some random direction that is a characteristic of the local manifestation of randomness at this point. So one can imagine, therefore, that randomness at the coarse-grained level can be regarded as a series of pumps that generalize the individual pump that we had before, except now that these pumps that are generated at the coarse-grained level from randomness are distributed at random locations and have random orientations. So we constructed what the effect of a single pump, let's say characterized by a force at location R alpha, on the density was, and it had this kind of power law effect that kind of looked like a dipole. And we can imagine that if we have many of those dipole forces, the resulting density can be obtained at some level by superposition of the modifications to the current that individual one of these pumps causes. So we have a formula that relates the density to a particular realization of random pumps. Over all realizations, we expect that the random pump at each location has no particular preferred orientation, and random pumps at different locations are independent of each other, introducing some kind of a variance sigma squared. And using that formula, we can average this density. The average variation is 0, but if we look at the average squared, and go to Fourier space, we find that the characteristics of density fluctuations in Fourier space have a power law decay as 1 over q squared. So this is very different from having a uniform liquid system, because in a uniform liquid system, you would not have divergences at q equals to 0. You would have something like a Lorentzian at most or something like that, that would go to a constant. So that means that if you start with a pure system and the particles kind of look like an average density plus fluctuations in density, but then randomize the surface over which they are moving, this quenched realization of randomness will create currents, and these currents, because they are extended over large distances, on average cause variations in density that have these power law characteristics in Fourier space. And so what you generate is this kind of correlated fluid in which you can see that essentially there are long regions that are kind of large regions that are kind of behaving in coordinated fashion. And essentially, another thing that happens is that there will be some currents that are frozen in the system. There will be quenched currents that go different ways. So it is like the randomness is constantly steering the fluid in some particular fashion.
Mehran, can I ask a question?
Sure.
So the landscape that you have here, right? So doesn't this behavior depend also on the nature of the landscape? Because every time you can have a landscape with some local minimum and some like maybe some deep minimum, and like the active particles, like the simple overdamped Brownian particles, they can also come and get stuck in all this kind of local minimum, and they need some certain amount of time to escape from them. Unlike the overdamped particle, which actually rely only of thermal fluctuations, here you have also additional persistence. So how do this work out together, the persistence and this thermal fluctuation, for them to actually explore the landscape?
That is an excellent question. So basically, the answer that I gave you, relying on things like superposition, etc., is clearly valid when the strength of the randomness that we are assuming is kind of weak. And once you have a situation such as the one that you mentioned, where there are strong potentials that for a long time can localize a particle before it can have, due to persistence or whatever, escape these potentials, there could be a very different regime. So I would not be surprised if, as a function of the strength and the form of the disorder, there is a weak regime, which is the one that we are discussing, and there is another regime that is kind of localized, in which maybe different parts of the system don't talk to each other or something like that.
Nice.
So that's certainly a good question that we haven't explored. And again, what we are simulating here is kind of at the limit of peak disorder.
Okay, thank you.
Okay. So let's, I should say that this was actually in the limit not only of big disorder, but very weak interactions among the particles. And so one of the things that we can ask is, first of all, forget about the weak disorder, but strengthen the interactions among the particles and see what happens. And one of the things that is known for the case of these active systems is this very nice concept of motility-induced phase separation. So the idea is that in this system that is simulated, you have essentially particles that follow this model of active Brownian particles that we mentioned. They have a velocity, they move around, but additionally, we have put an interaction between particles so that when they collide, they experience a force from each other. But the interesting thing is that the force is completely repulsive. So what is simulated are essentially active billiard balls. Billiard balls that have some particular size. They move in some random direction with the engine with velocity v until they change the orientation and they hit each other. And this is the result of the simulation. Now, the thing that is a little bit counterintuitive is that in equilibrium, if we have billiard balls with only repulsive interactions, we don't expect to see this kind of dense dilute phase separation, which is a form of condensation. Because in order to form a liquid state, you need the attraction between particles to overcome the loss of the entropy that they would have had in the gas state. But in this system, without any attractive interactions, the particles condense. And the cause of that is that essentially the particles, when they collide with each other, they don't immediately separate like ordinary billiard balls do, because their engines continue to push them together for a while. And it may be that before the chance they have to change their direction and move away, another particle comes in and jams them. And again, the image that I sometimes convey is that you are in a huge field of these bumper cars that are shown in entertainment, where kids on these cars are moving around. And very soon there will be big jammed configurations. And so this is an example of that. And this was described by Cates and Tayor very nicely in terms of just the combination of two phenomena that essentially in regions where there is more density, the particles slow down, and regions where particles have slowed down, density accumulates, so you have the means for an instability that is the cause of this motility-induced phase separation. Okay, so this is a nice phenomena that exists for these systems and is manifestation of interactions among these particles. Question is, what happens if we now go back and try to simulate this system on a random substrate? So now we add the randomness, be it very weak randomness, to this strongly interacting system of particles. Now, I would like to use an analogy to an equilibrium system. So condensation, we can usually describe through some kind of Landau-Ginzburg free energy. And there is some kind of a compressibility, and the compressibility, if it changes sign, you will have some instability that would require higher order terms in order to stabilize the density. Now, what happens if you try to add random chemical potentials that locally prefer the density to go up or down to the system, where these random chemical potentials have zero average and they have fluctuations. Now, this is precisely what our liquid would like to do. Our disorder wants to prefer some kind of a density variations that are kind of randomly distributed and have a characteristic power law because of the long range conservation. So in order to mimic that system, our chemical potentials must have this kind of long-range correlation. So then the question that one can ask is, suppose that I was looking at the system in equilibrium that was undergoing some kind of a phase transition because the compressibility was changing sign, but that system was subject to these random chemical potentials. Would condensation still take place or not? Now, this is a topic that back in the 1980s, people discussed in great detail in the context of the random field Ising model. And there is this celebrated argument due to Imre and Ma that showed that randomness destroys phase transition. The idea is the following. Imagine that you have a simple magnet where the spins want to point in some particular direction, and the color indicates whether you are in the up direction for yellow and in the down direction for blue. So in the absence of random fields that are indicated by these arrows, then you would have a nice phase separation between a large yellow domain and a large blue domain. So that's an example of a phase transition. What happens to the system if I now add these random fields that locally prefer one phase or the other? Now, maybe by chance, there is some region in space here indicated by size R, where the preference of the random fields is for a domain that is opposite to the domain that you had before. Would this preference cause this domain to flip from yellow to blue? The argument is as follows, that the typical loss that you would have in causing this flip is from the surface. There is a surface tension, and the cost of the surface tension goes proportionately to R to the d minus 1 in d dimensions. So that's this term, surface tension R to the d minus 1. Now, for ordinary random fields, which was the Imre-Ma argument, the gain was from the square root of the fluctuations in a volume of size R would have been R to the d over 2. Balancing R to the d minus 1 and R to the d over 2 would give you the Imre-Ma critical dimension of 2 for random field system that is correct. Our case is slightly more complicated because our random fields are correlated through this requirement that arose from the conservation law. And because of that correlation, the effect of the random fields is felt over a larger distance. And when we replay the argument of Imre-Ma, in addition to the square root of volume, we get an additional factor of R because of the long reach of these correlated random fields. Balancing these two gives us a critical dimension that is shifted from the value of 2 that one has for the ordinary Imre-Ma argument to 4, meaning that in dimensions below 4, if this argument that is based on equilibrium holds for our non-equilibrium motility-induced phase separation, would imply that this phase transition should disappear in dimensions below 4. So we go and do that for our system that is in 2 dimensions. In the absence of randomness, we have this nice behavior. Once we have randomness, then the system does not equilibrate, but goes over to the kind of correlated fluid that we had mentioned before in the presence of disorder. So disorder wins in some sense over the case of the interactions. This was quenched from high temperature. One can also start from the low temperature states, which would be something like this. You turn on the randomness, and the randomness essentially rips apart the ordered domains that one has. Or alternatively, one can start with no domains because of randomness, switch off randomness, and again, you form phase separation. Okay? So this was one consequence. Perhaps the more interesting consequence is the following. Imagine that we leave the bulk of the system completely free of disorder, but we add disorder to the boundary of the system and ask the question of what happens to this phase separation. Point again is that this disorder at the boundary can locally act as pumps that tries to create currents that go one way or the other way. And these currents will reach deep inside the material and will have influences on the densities that want to form here to form a condensate or not. And if we replace our in-Riemann argument with randomness that is not coming from volume, where we had here r to the d, but from surface that goes like r to the d minus 1, we find that the lower critical dimension still is high, shifts from 4 to 3, which means that in our two-dimensional system, essentially just roughening the boundaries should have a profound effect on what is happening in the bulk. That is, in the case of a passive system where you have this phase separation, what we are familiar with is that boundary, whether it is flat or rough, should have no effect on the bulk. But in the case of this disordered system, where in the absence of boundary disorder, the pureness, the lack of impurity in the bulk can create this kind of motility-induced phase separation, the impurities on the surface will reach over and destroy the long-range order in the bulk. And this is the movie that is sort of exhibiting that at t equals to 0, right now there is no disorder at the boundary. We introduce disorder at the boundary, and it kind of rips apart the ordered domain that was inside and destroys it. So this is a kind of another counterintuitive effect where the bulk ordering is modified by surface or disorder in this active system. So let me summarize. So basically, we started by talking about pressure in the language of the force that is acted on the boundaries. And we saw that in these active systems, this pressure depends on the walls of the container and can cause a system that is homogeneous to become spontaneously inhomogeneous. That even in the absence of asymmetry, the presence of activity causes the dependence of the force on the curvature and of the boundaries. And the dramatic manifestation of that is this passive filament that in the presence of activity spontaneously curves and starts to move in one direction and is countered by currents of the particles that are kind of pulled and pushed by this curved object as if it was a pump, that randomness can be expressed as a collection of these pumps, and a distribution of weak randomness as a collection of pumps creates fluids that are spontaneously stirred and have long-range correlations. And these long-range correlations can also destroy ordering that can take place in the bulk of the system due to this motility-induced phase separation. Whether the disorder is throughout the bulk or even just at the boundary of the system, because in some sense, the currents that are generated at the boundary reach out into the bulk and destroy the bulk order. So this work was done in collaboration with Julien Taillor, who's now a colleague at MIT, Yalif Kafri, who started these projects with me along with Alex Solon, who was a postdoc and is now back in Paris, a large number of very talented collaborators and students and postdocs, one of whom, Sung-Kan Rho, is now faculty at Harvard. And this talk is based on reviews of modern physics article that you can download from here and read. And I would like to thank all of you for listening to me and organizing this Boltzmann. I'm happy to take questions.
So let's first thank you, Mehran, for this very insightful talk. Thank you very much. The floor is open to the questions. So if people would like to ask questions, maybe add comments or say a few things, like there are students in the audience. I think just feel free to ask questions, and I think Mehran will be able to answer, like most of them with high precision and high clarity. Yeah, please go ahead if somebody has. Otherwise, maybe I will start.
Yeah, I have a question. Hello.
Yeah, please go ahead. We can listen to you.
Yeah, so in the case, so in current slide, this case 3, so I was wondering, so when the string is put in the active particles medium, so the active particles are still moving in random direction with the equal probability, but why it is so that the string is bending to one direction, it is not to the other direction? Why this bias is coming?
Okay, so maybe we go back here and take a look. So initially it is flat and the forces are completely random. So by chance, there happened to be more forces that were in one direction as opposed to the other direction. Once that happened and there was a curvature, then there were essentially more particles that were trapped on the curved side and more easily sliding off from the other side, as kind of indicated here. So particles in one side easily slide off, particles from the other side kind of get trapped, and they provide more force in one direction or the other. Now, as a function of time, because as you said, the forces are completely random, so it may be that some of these particles happen to move further away, the direction of curvature and the direction of movement changes, and this randomness is manifested even more at the scale of something that is longer, like here. I don't know if that answered your question.
Yeah, so, and okay, and also, like, for example, in the second case, when your like the string is too long, so how do you decide
Yes.
how do you decide if the string is too, like, can you tell a priori if the string is too long for this drift to be present or not? Does it
Okay,
depend?
so yes, no, that's interesting question, important question. So basically, any filament has a resistance to being bent. And that bending gives it what is called a persistence length. So for a certain amount of fluctuations, let's say from temperature, one can bend. If the fluctuations are weak, they don't really bend very much. If the fluctuations are strong, they can bend over a smaller radius. So that is called the persistence length of a polymer. So basically, given the certain amount of activities that one has and the properties of the filament, one can calculate a characteristic length scale, which is the persistence length, and the worm on the left is less than the persistence length in size. The worm on the right is longer than the persistence length in size.
Okay, I see. So the persistence length depends on the properties of the active forces that the particles are giving, and also, like, apart from the length, it also depends on the internal structure of the filament.
Exactly. Yes, that's exactly correct.
Okay, thanks.
So along this line, maybe I will also ask something. So when you have a rigid inclusion like what you have shown here, so is there a way actually to quantify, what would be the right quantification or a right observable to measure the amount of like that the particle will spend more time actually inside the inclusion than outside? Is there like some sort of a time that people can measure? I mean, because we can understand the overall effect of the movement of the inclusion towards one direction, that we understand. It's a collective effect that we see. But let's say that I just want to understand on a single particle level, like the particle comes and then there is an inclusion and it spends a lot of time inside because it has to flip and then come out of this, right?
Exactly.
So
Yeah.
what is the observable that I should look for, like in this kind of, if not the overall behavior, like near an inclusion, like?
Yes. So you are asking a very important question, which is that once I give you some microscopic model that these particles have a certain interaction with this U-shaped object, certain persistence, velocity, etc., size of the object, what is the macroscopic consequence? And the macroscopic consequence for us is characterized simply by one number, which is the strength of this dipole. So the question that you are asking is, given some microscopic model in which I know everything about the shape of this object, the motion of the particles, etc., persistence, everything, can I calculate this? And that's one of those to me, hard problems of making a connection between a microscopic model and a macroscopic variable. Kind of like if I give you for an Ising model, the interactions between nearest neighbors and next nearest neighbors, can you predict for me the transition temperature? Okay, you can use some kind of estimate and try to get something like that, but that is something that I guess requires a certain number of approximations, modeling, and then comparison of macroscopic and microscopic models.
Okay. I mean, along the line, I also always had this, I don't know, like lack of clarity, I would rather say, that the models usually we use for active particles is like run and tumble particles for bacteria movement and then the active Brownian motion that you showed. These are all phenomenological model, and by construction, we have terms which essentially will break time reversal symmetry. But we always talk about active engines is like something self-propulsion velocity which is being generated. But is there a microscopic, like even a more microscopic way actually to understand this, like how to because the real systems like inside like our body, we have like living systems, right? And we are modeling them by run and tumble motion, etc., etc. When I say run and tumble motion, I say that okay, the particle has a self-propulsion velocity and then it tumbles, etc. And then by default, by this construction, I of course break the time reversal symmetry. But a living system, need not know that this is a run-and-tumble system. This is a run-and-tumble model or active Brownian model. I don't know, like whether I framed the question properly. I just wanted to know, like, is there a microscopic way, even more microscopic way to see this time reversal breakdown of this time reversal symmetry for active systems? It need not be this particular kind of models, like generically. Because even for simple Markov, like I said, for simple random walker, by taking an asymmetric random walker, actually I can show a breakdown in time reversal symmetry, right? By just creating
Yes,
by creating a bias.
exactly. Yes, right. So if I understand correctly, you are asking the following question: that at the level of microscopic models, we can certainly construct rules that break time reversal symmetry, and maybe we can even observe that by looking at the difference between forward and backward paths, which is the standard way to sort of characterize this. Now, suppose that we don't have access to the individual motion of the particles, but we are looking at some collective variable, such as, for example, diffusion of a passive particle in this fluid, or we can look at something like density variations, response, etc. Is it possible that I would be able to see the presence of time reversal symmetry for these observable?
Right.
And I think that the outcome is kind of mixed, because if I look at the bulk of this system of active particles that we are simulating and just focus at a very coarse grained density and look at the response of that density, it kind of looks like a response of a fluid with some appropriate effective temperature, diffusivity, etc. So I don't see anything at that level. But then I put a corrugated wall next to it, and from the forces on the wall, I can see something. So there are some macroscopic observables that demonstrate the time reversal symmetry and some that don't. And that is kind of an interesting thing, that in some sense, under coarse graining, some aspects of this absence of time reversal symmetry are screened out and become irrelevant, and some other aspects are relevant. And that's what makes this an exciting field to continue to look at.
Yeah. Yes. Yeah, we'll wait for if there are other questions from the audience, from the students. Let me check the chat box. Okay, so there are no questions in the chat box. So maybe I will continue, because I need some clarifications. So you were discussing about the problem where the active particle essentially comes close to the wall, and then you apply the torque. And then I think you showed that regardless of the presence of the torque, whether you add them or not, you still see the the breakdown in the time reversal symmetry, right?
Again, what kind? So basically,
This one.
Yes, so this one does require the torque. So if I turn off the torque, because again, the formula for the pressure that we calculate over here, and I guess I'm going in the wrong direction, does depend. What's happening here? The formula for the pressure here does depend on the torque. So if I set the torque to 0, this pressure would be uniform, independent of the potential. But even in the absence of the torque, these effects would persist. Like you would have a current because of asymmetry, you would still have curvature dependence of the force, etc. So that's again another interesting observation, that some aspect of the microscopic model, whether or not you have the torque, has a manifestation about, say, the pressure difference or not, but in both cases, it has an effect on the curvature.
But the pressure, the form of the pressure, how crucial is the persistence? Like what is the ramification of it? Like if you have a strong, persistent random walker, like active walker, and how will the shape of this density? How will that change? Yeah, this is I wanted to understand this part. Right.
Well, this is the combination that appears. So this V is the V over D is related to the persistence length. D is the rate at which you rotate or change the change the angle. Yeah. So certainly all of those effects combine with the presence or absence of torque to determine the pressure difference.
Okay. Thank you. Let us see, like
I guess I have to leave shortly, so if you give me 1 second. Please come in. I have to finish something.
okay.
So if you don't mind.
Yeah, no problem. So as we can see that there are no further questions. So let us thank Mehran again. So Mehran, thank you very much again for giving us the time and also opportunity to listen to your talk. And I hope that we will have opportunities, all the students also will have opportunities to meet you in some other places elsewhere. Okay. Thank you very much.
Thank you very much for organizing this.